Betelgeuse has already exploded. Maybe. We just might not know it yet. Right now, while you're listening to these words, the light wave from the most magnificent cosmic firework in human history could be racing toward us through the void. It has already crossed 649 light-years out of 650. 1 light-year remains, 1 year until the night turns into day and a second sun ignites in our sky. The red supergiant on Orion's shoulder is not just a bright dot in the winter heavens. It's a cosmic bomb whose timer could go off at any. We live suspended in uncertainty, not knowing whether tomorrow we'll witness the grandest cosmic show in the visible history of the universe, or whether it will happen 1,000 years from now, when our descendants are already gone. But there are signs, strange, unsettling signs. The star has begun to behave unpredictably. It dims, flares, pulsates, as if scientists lose sleep at night, aiming telescopes at the hunter's shoulder, trying to decipher the death spasms of a dying giant. Because when Betelgeuse explodes, it won't just be a beautiful spectacle. For the ancient Greeks, it was the hand or shoulder of the mighty hunter Orion, a giant whom the gods lifted into the heavens. Arab astronomers called it Yad al-Jaza, the hand of the central figure. Over time, the name transformed and warped through translation and copying, turning into the word we know today, Betelgeuse. Try saying it out loud. Feel how your tongue stumbles over the syllables. Betelgeuse. There's something ancient in that name, something alien, like an echo from distant civilizations that all the ancients couldn't know that this light was a sign of dying, that they were witnessing the final breath of a cosmic giant stretched out over a millennium. When Renaissance astronomers began systematically cataloging stars, Betelgeuse received the designation Alpha Orionis, even though in brightness it often yields to Beta Rigel. That strange mismatch comes from the fact that Betelgeuse's brightness changes. It isn't constant like most stars. It breathes, swelling and contracting, becoming brighter, then dimmer. Ancient astronomers know hot stars glow blue or white. Cooler ones glow red or orange. It's like a flame. Its hottest part is blue. Near the base, where the temperature is lower, the tongues of flame are orange and yellow. But a cool star is only half the problem. At the beginning of the 20th century, astronomers learned how to measure the sizes of stars, and when they applied their new methods to Betelgeuse, the results shocked them. This star was monstrously huge. If you placed it where our sun is, its surface would reach Canaan, the orbit of a red supergiant. Is an unstable state. It is agony. It is the death throes of a star that has exhausted its resources and now bloats, trying to extend its existence, if only for a moment by cosmic standards. Betelgeuse is dying. It is dying right now before our eyes, though we see it as it was 650 years ago. 20th century astronomers began to understand what happens inside such stars. They built models, solved equations, ran thousands of computer simulations. The picture that opened before them was both beautiful and terrifying. Compression heats it further until the temperature becomes sufficient for the next reaction. Helium begins to fuse into carbon and oxygen. At the same time, hydrogen continues to burn in a shell around the core. The star seems to get a new life, but it pays dearly for it. The energy released by helium fusion is enormous, so enormous that the star's outer layers are literally thrown outward. The star swells. Its radius grows hundreds of times. Imagine a balloon that keeps being pumped up. The rubber stretches, grows thinner, and the balloon grows larger. The star becomes like a sprinter who started out running a marathon at a calm pace, but in the final meters gives everything, burning the last strength in a matter of seconds. Inside Betelgeuse now is a layered structure like an onion. In the center is a blazing core of iron and nickel. Around it is a shell where silicon turns into iron. Farther out is a layer where oxygen fuses into silicon, and so on, layer after layer, until you reach the outer envelope, enormous, rarefied, where hydrogen is still burning. This onion is unstable. Layers mix, convect, churn. Hydrogen into helium releases energy. Helium into carbon releases energy, and so on, all the way to iron. But fusing iron into heavier elements does not release energy. On the contrary, it requires energy input. Iron is the equilibrium point, the dead end of thermonuclear fusion. When iron builds up in a star's core, fusion stops, and then the finale begins. Betelgeuse's core right now may already be composed of iron, or close to it. We cannot look inside the star. Betelgeuse could explode tomorrow, or in 100,000 years, or, most chilling of all, it already exploded, and the light from the blast is already on its way. The distance to Betelgeuse is about 650 light years. That means the light we see today left the star in the 14th century, in 1370 to be precise. Europe was suffering the Black Death, a plague epidemic that wiped out a third of the population. China was experiencing the decline of the Yuan dynasty. The Aztecs were only beginning to, and the news will not come the way we're used to. Usually we learn about cosmic events from scientists' reports, from articles, from news. First, astronomers detect something in their telescopes, then analyze data, then publish results, and only then do we, ordinary people, read about it. But Betelgeuse's explosion will be different. Everyone will see it at the same time. No telescopes, no observatories. Just step outside at night and look at the sky. In Orion, where a reddish star used to shimmer, a new point of light will flare. At first it will. At night, the new star illuminates Earth so that you can read a book without a flashlight. Its shadows are sharp, crisp. The sky isn't black, it's dark blue, like deep twilight. This will last weeks, maybe months. Gradually, the new star will dim, but even a year after the explosion, it will still be visible to the naked eye, a bright point where Orion once was. But before that moment, events will occur that we won't see, but we'll learn about thanks to science. A few hours before the flash becomes visible, neutrino detectors around the world will go crazy. When Betelgeuse's core collapses, so much energy is released that most of it is carried away precisely by neutrinos. They burst from the collapsing core and race at the speed of light in all directions. A few hours after the collapse, they will reach Earth, and detectors will record it. Scientists will see a sharp spike on their graphs. They will understand the thing they have awaited for decades has happened. A supernova, and it is close. So close that the detectors will practically choke on the number of neutrinos. An alert will be declared. Around the world, astronomers will aim telescopes at Orion, so humanity will have a small window, several hours, between the neutrino detection and the visual flash. Several hours to prepare, to tune instruments, to notify the world. This is happening. Neutrino detectors are scattered across the globe. They are hidden deep underground, in mines and tunnels, where cosmic rays and other interference don't prevent catching these elusive particles. One of the largest is in Japan, in an abandoned mine under a mountain. A huge reservoir of ultra-pure water, surrounded by thousands of sensitive sensors. All telescopes swing to the coordinates from which the neutrinos came. Observation begins of the greatest cosmic event in human history. Now let's understand what exactly happens at the moment of explosion. Why does a star explode? What triggers this cataclysm? To understand, you must imagine the star's internal structure in its final moment. The core consists of iron and nickel. It is roughly the size of Earth, but with a mass about 1.5 times the mass of the Sun. Imagine a sphere the size of our planet, but so dense that its mass exceeds the mass of an. On the other side, electron degeneracy pressure resists. This is a quantum mechanical effect the same stellartrons cannot occupy the same state. They repel each other on the microscopic level, creating pressure that holds the core up against collapse. As long as thermonuclear reactions continue in the core, additional energy is released, also helping resist gravity. But when iron accumulates, reactions stop. Energy is no longer released. Only electron pressure remains, and it begins to lose the battle. The mass of the outer layers presses harder. Imagine the entire Earth-sized sphere shrinks to the size of a city in a fraction of a second. In 1 second, the core becomes thousands of times smaller. Density skyrockets to unimaginable values. Protons and electrons are squeezed so strongly that they merge, turning into neutrons. A neutron star is born, a ball of pure neutrons so dense that a teaspoon of its matter would weigh billions of tons. Or, if the core mass is large enough, collapse doesn't stop even there. The core continues to compress until it becomes a black hole, but at the moment of collapse, so much energy is released. At the same time, an enormous number of neutrinos born during the conversion of protons into neutrons carry away energy. Part of that energy is transferred to the matter, additionally driving the blast wave. The star's outer layers literally evaporate. They expand in all directions, forming an expanding shell of superheated gas. That shell glows heated to millions of degrees. There is so much energy that the flash outshines an entire galaxy. If Betelgeuse exploded in our galaxy, news will spread through scientific circles and online, but not everyone follows astronomical events in real time. And then, a few hours after the neutrino spike, someone who happens to glance at the night sky will notice a new star. It will be bright, very bright, brighter than Venus, brighter than Jupiter. In just minutes, as the person watches, it will get even brighter. They will call others. People will step outside. A storm will erupt on social media. Photos of the new star will flood the internet. Everyone will ask, "What is it?" Orion will be changed forever. Instead of the reddish shoulder of the hunter, an intense white point outshining everything around. But it won't last forever. After a few weeks, the brightness will begin to fall, slowly at first, then faster. After a month, the supernova will still be visible to the naked eye, but not as bright. After 3 months, it will resemble an ordinary bright star. After half a year, you'll need binoculars. After a year, you'll need a telescope. And after a few years, a nebula will remain in its place. They will look for traces of different elements synthesized during the explosion, because a supernova is not only destruction, it is creation. At the moment of explosion, temperature and pressure become so high that reactions begin which are impossible under normal conditions. Heavy elements that could not form in the star's ordinary fusion reactions are born in the fire of the blast. Gold, platinum, uranium, all elements heavier than iron are created precisely in supernovae. Every atom of gold in your jewelry, every atom of... But Betelgeuse will be so close that we'll see details previously inaccessible. It will be a scientific breakthrough. The data collected during the explosion will be analyzed for decades. The event will enter textbooks, become a reference point in astrophysics. And what about danger? Many have heard scary stories that a supernova explosion can destroy life on Earth. How real is that in the case of Betelgeuse? Let's break it down. A supernova really can be dangerous. It releases an enormous amount of energy in radiation. Betelgeuse is about 650 light-years away, about 6 times farther than the critical distance, far enough that we don't have to fear catastrophic consequences. Yes, we will get a dose of radiation. Satellites will detect spikes of gamma and X-ray, but the atmosphere will protect us. It will absorb most of the hard radiation. Only a small addition will reach the surface. No more dangerous than an extra X-ray at a clinic. But there is one more factor: gamma-ray bursts. These are narrowly focused jets of radiation that can accompany. Even if a gamma-ray burst occurs, it will miss us. We'll see the flash, but we won't receive a deadly dose. So Betelgeuse's explosion will be safe. This is important to understand because when it happens, rumors, panic, and conspiracy theories will spread. Someone will say it's the end of the world, that radiation will kill everyone, that governments are hiding the truth. Don't believe it. Scientists say honestly, yes, it's a grand event, but no, it does not threaten Earth. We are at a safe distance. The only thing that will change, but at the end of 2019, the brightness dropped more than expected. Much more. By February 2020, Betelgeuse had dimmed by more than half compared to its usual brightness. It was visible even to the naked eye. People familiar with the winter sky noticed that Orion's shoulder had become noticeably paler. Astronomers sounded the alarm. Was this it? Was the star preparing to explode? A frenzy began. Telescopes around the world were aimed at Betelgeuse. Observations were conducted across different ranges: visible, infrared. By April 2020, Betelgeuse began to regain its brightness. By summer, it was almost back to normal. Many sighed with relief. A false alarm. Others, on the contrary, were disappointed. They wanted to see an explosion, if only for scientific curiosity. So what really happened? Data analysis showed that, most likely, the star Rilti Nituali ejected an enormous cloud that then cooled, turned into dust, and partially blocked its light. This was supported by infrared observations, where dust glowed. This material forms a nebula around the star that can be observed in telescopes. But sometimes, the ejections are larger. A huge bubble of plasma bursts from the surface, cools, and dust grains condense inside it, tiny solid particles made of carbon, silicon, and other elements. This dust absorbs the star's light, making it appear dimmer. So the great dimming of 2019 was probably not a harbinger of an immediate explosion. It was normal, though unusually large. Models of stellar evolution give a wide range from a few thousand years to 100,000 years. That's enormous uncertainty. Why is it so hard to predict? Because the processes inside massive stars in their final stages are incredibly complex. Everything depends on details: exact mass, rotation rate, magnetic fields, convection, mass loss. Small changes in these parameters can shift the moment of collapse by tens of thousands of years forward or backward. And many of these parameters cannot be measured precisely. We can't weigh the star's core. If the star began to lose mass faster, ejecting more and more material, that too would be an alarming sign. Some models predict that shortly before collapse, a red supergiant may temporarily shrink, become hotter and bluer, then expand again. If we saw such behavior in Betelgeuse, it would be a strong hint. Another way to learn of an approaching explosion is neutrino detectors, but there's a nuance. Neutrinos born in ordinary thermonuclear reactions in the star's core cannot be detected at that distance. There are too few. That is why scientists watch the star so carefully. Every unusual behavior is recorded, analyzed, compared to models. Maybe the key is hidden in these data, a way to predict the explosion at least weeks or months in advance. Maybe not, but the observation process itself Accumulating data is valuable because when the explosion happens, those data will help us understand what preceded the catastrophe. Future astronomers studying the archives will say, "Here, 6 months before the explosion, something happened and we didn't notice." Or we noticed, but Betelgeuse will leave its mark, an expanding cloud of gas glowing in different colors thanks to radiation from internal processes and from the central object. And what will be in the center? A neutron star or a black hole? That depends on how much mass remains in the core after the outer layers are expelled. If the remaining core mass is less than roughly 2 to 3 solar masses, a neutron star forms, a sphere about 20 kilometers in diameter, made almost entirely of neutrons. Its density is so extreme that a teaspoon would, and if those beams point toward us, we see a pulsar, a source that flashes with a very precise period. Perhaps Betelgeuse will become a pulsar, and we will be able to observe it, hear its radio signal, a cosmic lighthouse pulsing with incredible regularity, the voice of a dead star, an echo of its former power. But if the core mass is too large, collapse doesn't stop even at the neutron star stage. Gravity becomes so strong that no force can resist it. Collapse continues, and the core. From the supernova's light curve, spectra, and emission behavior, scientists will determine what remains at the center. If they detect a pulsar, that confirms a neutron star. If there is no pulsar but there are signs of accretion, matter falling onto a central object with the release of huge energy, that may indicate a black hole. Either way, we will get an answer to a question that is open today. And what about culture, society? This event will enter human history. It will become as significant as the discovery of America, the moon landing, the invention of the internet, because it is a cosmic scale event. Religious thinkers will see a sign, a symbol. Some will say it foretells the end, others that it marks the beginning of a new era. People will gather in groups to watch together. Astronomy clubs will organize mass observations. Observatories will be packed with visitors. The internet will explode with discussions, photos, videos. It will be a global event, uniting humanity in a shared experience of cosmic wonder, and it will remind us how small we are before the universe. A star that existed for millions of years, a giant among stars, that material then participates in the formation of new stars, new planets. The cycle continues. We ourselves are part of this cycle. Every atom in your body was once part of a star. The carbon your cells are made of was synthesized in the core of a red giant billions of years ago. The oxygen you breathe was also born in a star. The iron in your blood was created in the final moments before a supernova exploded. You are stardust assembled into a conscious form, and when Betelgeuse explodes, it will create new. We are connected to the universe at the most fundamental level. Our existence is possible only because other stars once died, creating the elements from which Earth and all life formed. Betelgeuse will remind us of this connection. There is one more aspect worth considering. What if the explosion already happened? Remember, light takes 650 years to reach us. Imagine Betelgeuse exploded in the year 1500. Columbus has just discovered America. The Renaissance is in full swing in Europe. Leonardo da Vinci is painting, or the explosion will happen in 100 years. We won't see it, but our descendants will. Or in 1,000, 10,000. We don't know. And that knowledge, or rather, that not knowing, adds a special sharpness. We live in anticipation. Every night could be the night when a new star ignites in the sky. Astronomers joke that watching Betelgeuse is like waiting for a balloon to pop. You know it will pop, but you don't know when. You can sit and stare for hours and nothing happens, or you can look away for a second, and in that moment, if a star's brightness changes sharply, the system automatically sends notifications. Astronomers subscribe to these alerts. They will get a message on their phones. Betelgeuse has flared. And then the race begins. Everyone will want to point their telescope first, get the first spectra, the first data. It will be competition and cooperation at the same time because we need a lot of data, and the more telescopes observe, the better. Even now, there are plans for coordinated observing campaigns. Astronomy organizations worldwide have agreed. When Betelgeuse explodes, these telescopes and all these data, all these observations will give us an unprecedented understanding of what happens in a supernova explosion. We will learn details we could previously only guess. How exactly does the shock wave propagate? How do the star's layers mix? What elements and in what quantities are synthesized? How does a neutron star or black hole form? How does the expanding shell interact with the surrounding medium? All these questions will find answers. Scientists will test their models, see what they predicted correctly and where they were wrong. And that life will exist because Betelgeuse once died, enriching the cosmos with heavy elements. Death and birth are intertwined. One is impossible without the other. That thought should calm us. Yes, we are mortal. Yes, everything we know will one day disappear. But the matter we are made of will continue to exist. It will take other forms, enter other structures. The atoms of your body will someday become part of stars, planets, maybe other living beings. In that sense, we are immortal. The Doppler effect smears the lines. Part of the gas moves toward us, part away. The lines shift blueward and redward. A few weeks later, when the outer layers become more transparent, we will see deeper layers, lines of oxygen, carbon, silicon. These elements were synthesized in the star before the explosion during normal fusion reactions. Their presence will confirm that we are observing the collapse of a massive star, not some other kind of supernova, because there are different types of supernova. Those that occur in massive stars are called nickel turns into cobalt, cobalt into iron. Each decay releases energy that heats the gas and makes it shine. Astronomers will measure expansion speeds of different layers, determine their masses and temperatures. They will build a three-dimensional model of the explosion, showing how material is distributed in space. Modern simulations already produce approximate images, but real data will calibrate those models with unprecedented precision. We will learn how symmetric the explosion is. Theory predicts supernova explosions are often asymmetric. Material is it. We will see how the wave moves through the nebula, how it compresses and heats the gas, how complex structures form, filaments, knots, rings. This interaction can also tell us how much mass the star lost before the explosion. The denser the nebula, the more mass was shed. By measuring the brightness and spectrum of the interaction emission, astronomers can estimate how much material Betelgeuse expelled over the last thousands and millions of years. That matters for understanding massive star evolution. Mass loss influences what final remnant forms. That will give information about magnetic fields and about populations of relativistic particles, electrons and protons accelerated to speeds close to the speed of light. We might also detect gamma rays, but not from the initial explosion, rather from the remnant. If a rapidly rotating neutron star with a strong magnetic field forms in the center, it can act like a gigantic particle accelerator. Particles accelerated in the neutron star's magnetosphere interact with surrounding gas, producing gamma radiation. Space gamma telescopes could detect it, evidence of central object activity. The signal would be weak. The distance is still large by gravitational wave astronomy standards, but detectors keep improving. By the time Betelgeuse explodes, perhaps a new generation of detectors with greater sensitivity will be operating, and then we may have a chance to hear the gravitational whisper of a dying star. That would be extraordinary. Simultaneous detection of light, neutrinos, and gravitational waves from one source would open a new era of astronomy. We could compare arrival times of different signals. Observing a nearby supernova would provide experimental tests of those laws, helping refine, for example, the equation of state of nuclear matter, how pressure depends on density at extreme conditions. That is crucial for understanding neutron stars, black holes, and the early universe. In addition, supernovae play a key role in galaxy evolution. Their explosions inject energy and material into interstellar space. That energy heats gas, creates shock waves that compress gas clouds and trigger new star formation. This is called, without that, life as we know it would be impossible. But supernovae can also be dangerous. Hard radiation and cosmic rays from nearby explosions can sterilize planets, wipe out life. There is a hypothesis that some mass extinctions on Earth may have been caused by nearby supernovae. For example, the extinction at the end of the Ordovician period, about 450 million years ago, may be linked to a nearby supernova flare that destroyed the ozone layer and exposed Earth's life to a lethal dose of ultraviolet. Betelgeuse's explosion. This knowledge helps us evaluate the probability of life in different parts of the universe. Now let's talk about how Betelgeuse's explosion would be perceived by people without scientific training, ordinary observers. For many, it will simply be a beautiful spectacle, a new bright star in the sky. People will go out in the evenings to look at it, take photos, share them in social media. It will become a topic of conversation, a reason to gather. Families will meet in courtyards, gazing upward. Parents will tell children about stars, about It will be difficult, but important, because panic can be destructive. Fortunately, in the modern world, we have tools for fast distribution of accurate information. Science channels, bloggers, journalists will be able to deliver facts quickly. Explainer videos will gain millions of views. People will want to understand what is happening, and if information is accessible and clear, most will calm down and simply enjoy the spectacle. For children, this event may be life-defining. Imagine a child who, in 100 years, people will remember that in the 21st century, a supernova flared in the sky, visible to the naked eye. It will become a cultural marker, a symbol of the era. Artists will depict it, writers will mention it in novels, composers will write symphonies inspired by cosmic fire. The event will weave into human culture the way comets, eclipses, and other celestial phenomena did in the past. And perhaps it will make humanity rethink its place in the cosmos. We live on a small planet orbiting an ordinary star in a corner of a galaxy. The universe. We are part of the universe that has become conscious of itself, and that is astonishing. Betelgeuse's explosion could also become a catalyst for space programs. When millions of people around the world step outside to look at the new star, they will feel a connection to the cosmos. They will understand that space is not an abstraction, not something distant and unreachable. It is reality that can touch everyone. And that realization might push society toward greater support for space research. Imagine, after the explosion, it becomes real, tangible, personal. Everyone who sees the supernova will feel part of something larger, and that feeling could transform society. Of course, there will be skeptics, those who say, "So what? A star exploded. That changes nothing in our lives." We need to solve problems on Earth, not stare at the sky. And there is truth in that. Earth has many problems: poverty, disease, conflict, ecological crises. All of that needs attention and resources. But space does not distract from Earth's problems. Now let's imagine more concretely how the sky will change after the explosion. In the first days, the supernova will dominate. All constellations will fade into the background. Eyes will be glued to the blinding point in Orion. But gradually, as it dims, people will realize the sky has changed forever. Orion is no longer symmetric. One corner shines brighter than before. Even when the supernova fades to the level of an ordinary star, it will still be brighter than old Betelgeuse, and it will not be red, but white or bluish. For amateur astronomers, a new era begins, and who knows? Perhaps in 100 years, technology will allow us to send a probe to the remnant. The distance of 650 light-years seems impossible now. Even light takes centuries. But imagine a ship that can move at near light speed, or even more fantastically, one using space-time deformation, a warp drive. If such technologies are ever created, one of the first targets would be Betelgeuse. Scientists would want to see the remnant up close, fly through the nebula, collect samples, detect the neutron star or black hole, and study it in detail. And at that time, in space, the light wave from an explosion that happened 650 years ago crosses the final kilometers to Earth. It races at the speed of light, 300,000 kilometers Harakia. In 1 second, it can circle Earth 7 times, and then it enters Earth's atmosphere. Photons begin interacting with air molecules. The first observers are automatic telescopes that scan the sky every night, measuring stellar brightness. One telescope, say in the Atacama Desert in Chile, makes another measurement. The camera, an astronomer at the Paris Observatory, sees the alert and can't believe it. She calls colleagues. A chain reaction of calls, messages, emails begins. The astronomy community comes alive. But ordinary people still don't know. The family keeps eating dinner. The child asks permission to walk the dog before bed. The parents agree. The child gets dressed, takes the dog on a leash, goes outside. It's cold. The sky is clear, cloudless. Stars are bright. The child recognizes familiar constellations. There's the Big Dipper. But the fact remains, in the couple of minutes the child watches, the star becomes noticeably brighter. Now it's the brightest in the whole sky, brighter than Sirius, brighter than Venus, that you sometimes see in the evening. The child runs back home, bursts into the apartment, shouts, "Mom, Dad, come look, something strange is happening in the sky." The parents get up, confused. "What is it?" The child drags them to the window and points. "Look. There." It's not just a bright point. It's a cosmic catastrophe happening 650 light-years away. A star that existed for millions of years has just died, and they are witnesses. The mother hugs the child. The father calls friends, neighbors. "Did you see it? Look at the sky." People come out of their homes. Across the street, across the city, across the country, across the world, people step outside and stare upward. Someone brings binoculars. In binoculars, you can see that the new star is not a point, but a tiny disk. It is already so the distance is far enough. Enjoy the spectacle. This happens once in 1,000 years. The night passes. By morning, the new star is visible even at dawn when the sky brightens. It shines against a pale blue background. People go to work, to school, but everyone keeps glancing upward. Someone stops in the street, points. Strangers talk to each other, discussing the phenomenon. The usual social barriers fall away. Everyone is united by a shared experience. In schools, teachers cancel lessons and take children outside. The sky is not black, but dark blue. Stars fade against the new brightness. The Milky Way is nearly invisible. All attention is fixed on one point: Betelgeuse. Animals behave oddly. Birds that usually fall silent at night begin singing, thinking dawn has come. Dogs howl while staring at the sky. Cats sit on windowsills, hypnotized by the new star. Even wild animals in forests sense the change. Nocturnal predators come out earlier than usual, disoriented by the unnatural light. It's a record. Never before have so many neutrinos from a supernova been recorded. The data are analyzed. They will tell us what was happening in the star's core at the moment of collapse. Temperature, density, dynamics. Days pass. The supernova reaches peak brightness and begins slowly fading. But even after a week, it is still the brightest object in the night sky after the moon. People grow used to the new reality. Each evening, they step outside and check. The shell grows. Each day, it becomes larger. Professional telescopes capture detailed images showing structures, filaments, knots, irregularities. The shell is not perfectly round. It is asymmetric, as models predicted. Astronomers measure its chemical composition. Spectra show lines of oxygen, carbon, silicon, iron. Confirmation: we are seeing the star's insides, layers that were once hidden deep beneath the surface. The explosion turned the star inside out and scattered its... New editions of constellation guides show Orion with a changed shoulder. After a year, the supernova is visible only through binoculars or a small telescope. For ordinary observers, it blends into the background of stars. But astronomers keep watching. Every night, dozens of telescopes around the world are pointed at the remnant. Data accumulate. Every spectrum, every image adds a piece to the full picture. Scientists write papers. In the first year after the explosion, thousands of scientific works about Betelgeuse were published. It becomes the most studied supernova in history. They take long exposures, collecting light for hours. They produce stunning images and post them online. Astrophotography communities flourish. Everyone wants to capture Betelgeuse's remnant in their own way, find a unique angle, highlight details. It becomes something like art, scientific photography turning into an aesthetic experience. In the center of the nebula, scientists try to detect the core remnant, a neutron star or a black hole. This is difficult. The center is bright, filled with hot gas glowing in X-rays. X-ray telescope astronomers measure its magnetic field, the rate at which its rotation slows, its emission spectrum. All these data help us understand neutron star physics. But Betelgeuse's story doesn't end there. The nebula keeps expanding. Every year, it grows larger. 100 years after the explosion, it will cover a patch of sky several moon disks across. It will be faint, visible only through telescopes. But for astronomers, it will remain crucial because it is nearby, because we observed it from the beginning, because we have a complete dataset from the instant of the explosion. How will the explosion affect us in the long term? First, it will be a powerful educational impulse. Children who see the supernova will grow up with a deep interest in space. Many will become scientists, engineers, researchers. They will drive science forward, make discoveries, build ships that someday might reach the stars. Betelgeuse will become an inspiration source for an entire generation. Second, it will strengthen international cooperation in science. Betelgeuse's explosion, that's a philosophical thought, but it can have practical consequences. People may begin to value what they have more, care for each other more, Think more about future generations. Of course, this sounds optimistic, maybe too optimistic. Reality is always more complex. But even if Betelgeuse's explosion has at least a partial effect in that direction, it would already be huge, because the cosmos has the power to change us. When we look at the stars, we don't see just points of light. We see our history, our origin, our future. We see what. Imagine 1,000 years from now, when people, or their descendants, perhaps changed beyond recognition, look at the sky. They will see the remnant of Betelgeuse. They will know the story, how in the 21st century, or whenever it happened, their ancestors watched the explosion, how it affected society, what discoveries were made. That story will become part of humanity's collective memory, just as we now remember the supernova of 1054 observed by Chinese astronomers. And maybe by then, humanity will be an interstellar civilization, waiting for the light from an explosion that may have already happened to reach us, or waiting for the explosion to happen in the future. We don't know. And that not knowing makes the waiting sharp, thrilling. Every night is a possibility. Every time we look at Orion, we check. Still there? Still the reddish shoulder of the hunter shimmering in its place? For now, yes. But someday, the answer will be different. Someday, we will look up, and instead of the familiar red star, we will see a blinding flash, and then a new era